Hey guys, my name is Ben. I work at Virginia Tech Applied Research Corporation as a data visualization engineer, and I'm here to talk to you about graphs. But just so you know, I mean, you might not want to follow along, or you might want to follow along, but all the information that we're going to go over today, the code, the slides, can be found on my repository, Benjamin Ortiz Ulloa /DC PyData 2018. So if you want to play around with the code, if you want to explore it, there's a there's a Jupyter notebook there to play around with. Just to have fun. OK, so let's start out. So the format of this talk is going to be, I'm going to go over the following things. Basically, I'm just going to go into introduction, what is a graph? Then I'm going to go into practical applications, like how to make a recommendation system with a graph. I'm going to follow up with like an understanding of like the measurement and impacts, the measurements of impact and importance of a graph, or of the nodes of the graph. Follow that up with an understanding of how to use these metrics to actually like extract key phrases from a corpus of documents. And then I'm going to briefly explain what a agent-based model or a network model is. And then we're going to go over some code, and then I'm just going to close off with a few announcements. OK, so what is a graph? So a graph is made up of things, and things are also known as nodes and edges. Nodes and edges are essentially this different words for the same thing. These things are connected to each other with relationships, also known as links and edges. These relationships can have direction. So if you think about Twitter, I can follow somebody. They don't necessarily follow me back. That's a directed relationship. And there can be multiple relationships between two things. So I can follow somebody, they can follow me back, or they don't. That's the direction, and that's the multiple connections between two people. So a cool thing about graphs is that each of these things, whether it's an edge or a node, they can all store, and even the graph itself can store data. So if you actually have people as nodes, they have hair colors that can be stored in the node. They have jobs, that could be stored in the node. They have any kind of history, anything that could be like saved on an entity or a relationship can be stored in a node or an edge. And the cool thing about these attributes is that it can actually be visualized into a graph. So why do we care about the relationships in a graph? Well, it's basically because they provide context. So you have like two people that are friends or they like each other, but what does that mean in the greater scope of the network or the graph? So like two people who like each other, they could like each other because they have the same friend group or they hate the same person, right? That's a way that people can actually bond, and that's actually pretty well known in like social networks. So let's think about this, networks are dynamic. I'm not always the same friend with the same people. Sometimes we fall apart, or I get really mad at somebody and I really don't want to be friends with them. So what happens when that happens? What happens if I stop liking somebody? What happens if I get mad at somebody? What happens to my friend group? What happens to the actual graph? Well, in this example, you don't really know, because it's a really small graph, but we don't have more context. However, if we actually see the full network, we can kind of like infer what's going to happen. If my friend group is not contingent on the person I dislike, then I'm in a good place. Like, I'm probably going to still have my same friends. However, if the other person who I started to dislike was not as embedded in that friendship group, that person is probably going to get ostracized from the group. And that's one way to actually analyze a social network or any kind of network in general. So another cool thing about nodes and edges and node attributes is a node attribute could actually be stored as its own node. And this is another way of actually calling this is a bipartite graph. So if I have an attribute like a hair color, that hair color could actually be its own node. That attribute could be its own node. And we could actually use that to infer similarities or some kind of indirect connections between two entities. So here, we have certain nodes that are circles, certain nodes that are color blue, and certain large nodes. And we actually use that to actually make an indirect connection. And then we can project that into the actual, its own little graph, its own little subgraph made from these indirect connections. So we just talked about like a structure of a graph and actually just kind of like the architecture of a graph. That in its own right is enough to create a recommendation system. And like the reason why recommendation systems are important is because, well, like a little study came out a little while ago saying 35% of what consumers buy on Amazon and 75% of what users watch on Netflix come from product recommendations. So that's these are product-oriented companies, so that's a big impact on their business. So recommendations are important, especially if you care about selling things, if you care about like people continuing their subscription to your service, you want to do whatever you can to actually keep them going, and a recommendation system is a way to do that. And so the cool thing is just analyzing the structure, just following nodes and edges in the graph is enough to actually do this, and I want to explain how. So a way to do this with content-based recommendation systems is, let's say I bought an iPhone or an iPod. What is an iPod? Well, an iPod is an Apple product, and it's a musical product. So let's say in my inventory, I have other products that are both Apple products and musical products. So there's the Mac computer, there's the earbuds, the Mac earbuds, and then there's just the Bose earbuds. What should I recommend? What should be recommended to the person who bought the iPod? Well, there's only one thing that actually has has the most attributes in a relationship with the iPod, and that's the Apple earbuds. And so we're going to recommend that because of simply just the amount of connections it shares with the product that I've already bought. And there's another way of doing this called collaborative filtering. So I bought both a Mac computer and an iPod. Who are other people that bought these things? So there's one person who bought just the Mac computer, and there's one person who bought both products as the same thing. And so we could use that as a proxy to understand that I am similar to the person in the bottom right. And because of that, I'm going to suggest the other thing that that person in the bottom right has bought that I have not bought. So that's another way to actually form a recommendation system simply on like what people bought. And that's, again, this is just the structure of the graph, and we're following the graph, and we can already like get a lot of insights simply by following the connections. So graphs can get really large, and it becomes difficult to actually realize what's an important node, what's an important agent within that graph. And the way we can actually identify the important nodes in the graph is through these measurements. So before we actually go into some of the measurements, a lot of these measurements are dependent on a thing called are dependent on shortest paths and diameters. So a shortest path between two nodes is the traversal of like an edge and a node from one to the other that is actually takes the least amount of hops. So you'll see here, this is the largest shortest path. So that these are the nodes that are like farthest from each other. And so if we follow it, this will show us like how wide the graph is, and that's also called the diameter. So if we analyze all the shortest paths between all vertices, like every single vertice and their path to every other vertice, you'll start seeing seeing a lot of vertices popping up, showing up a lot, and those would be called those would have the higher betweenness centrality measurement. The betweenness centrality measurement simply says if you're in all the most shortest paths, you are more important. And again, because graphs can be directed, if it's a directed graph, simply like the shortest connections isn't necessarily important. You have to follow the actual arrow. So it's a shortest connection between arrows that'll show you the highest betweenness. There's also the degree, which is simply the number of nodes a single node is connected to. So if I step out once, if I step out from one node to another node, how many nodes am I going to potentially jump into? And that depends. That again depends on the direction you care about. I could be on Twitter. I can follow a lot of people. Not a lot of people are following me. So that means I have a very high out degree because if the direction of my following is going outwards, I have a huge out degree, not so big of an in degree because not so many people are following me back. And these can actually be shown in the graph itself. And you can just find general degrees as well. If you don't care about direction, then you can just find out all the connections you have. And another thing is closeness. Closeness is how close you are to every other edge. It has the minimal shortest paths to every single other node in the graph. And again, direction matters. And then there's hub scores, which if in the days of the early days of search and in the internet, a hub was considered a website that actually pointed to other websites a lot. So if you think about Wikipedia, Wikipedia does have its own content, but a lot of the value in Wikipedia is that it points you to other things. It references other websites and it references other things. And those things that it references are called authorities. So if you have a lot of websites pointing to you, if you have a lot of important websites like Wikipedia pointing to you, or if you are considered an authority would be actually a main website. So the authority on Ford cars would be the Ford website. That would be an example of that. Ford doesn't necessarily point to other websites, but a lot of websites will point towards forward if they came out with like a giant press release. And a combination of these things. So like the hub score and the authority score are very much connected. A combination of that, and this is what made Google pretty famous, is something called a page rank. So hub scores and authority scores are their own separate metric. A page rank kind of combines those two into a single metric. Basically saying like it's both important. It's important because it got pointed to, and it's important because it's pointing to a lot of other important things. And so these metrics can actually be used because these metrics are important in like whether it's like traversing the websites or whether it's traversing social networks, but it can also be used on other things like text. So we're going to actually analyze the PyData About Me page. So this is the information on PyData. PyData conferences bring together users and developers of data analysis tools. Text. There's text here. And the cool thing about text is that it actually has a natural flow of things. So if you actually follow a text from the first letter to the second letter to the third letter, if you just actually create an arrow between words, that's going to create the graph for you. And we're going to actually create that as a text graph, and then we're going to iterate over it. We're going to only keep the words that are both nouns and adjectives. We're going to run a PageRank algorithm on that text graph, and then we're only going to keep like the top third page ranked vertices. And that's going to provide us with, if two words are still connected after this, that's going to be considered a key phrase, and we're actually going to pull that out. This is the text rank algorithm. So this is an example of this is the first sentence in the PyData page. This is an example of like this is how you would actually form the graph. Now let's actually look at what it looks like when you have all the text from this PyData page. And this would be the equivalent of the full text graph for PyData. If we run that on the PyData page, we get these two key phrases. We get community gathers, which might not necessarily be a good phrase, but we also have analysis tools, which is absolutely a big point of PyData. So that's like that's really cool, and this is like a directed version of it. So like again, text rank could be either directed or undirected, depending on the algorithm you use. If we actually pull the undirected algorithm, we get these key phrases from the PyData side. We get the topical workshops, we get package developers, we get evolving challenges, PyData community, and community-driven conference. These are absolutely key phrases that should and can be pulled out from the PyData website simply by traversing a graph, simply by doing a graph metric or a simple graph algorithm on text on a single web page. And the same thing can be done with the code of conduct. The only word that got pulled out of the PyData's code of conduct is different backgrounds. That's the only key phrase that got out from the directed text rank. And the undirected text rank has other stuff. Like exclusionary jokes is a concept, tolerate friendly event, professional audience, body size, gender identity. Those are all the concepts that just got pulled simply by traversing the graph. And so the next thing I want to talk about is like graph models. This is a lot of fun, and this is stuff I'm like just exploring right now. So there's an idea that like because you can store attributes into a node, and you can actually change those attributes with time, you can actually follow the changes of these nodes and actually see how they affect each other. So in epidemiology, there's this concept of contagion models, and it starts off with a simple thing like certain nodes are infected, certain nodes are susceptible. If a susceptible node is connected with an infected node, the next time period that you're actually iterating over, those susceptible nodes will become infected. That's that's a simple SI model where it's called susceptible and infected. So if you're connected by a susceptible node, if a susceptible node becomes infected, then it infects. It's in the next t time that it affects the other connected nodes. So here is a simple a network where there are 3 communities of 25 people. Each community is connected by 2 edges. And like these 75 nodes get completely infected. This entire graph is completely infected in simply 4 steps. But there's more to it than that. Oh yeah, also, because we actually have the total number of nodes in this network, we can actually pull up more information. What is the percentage of infected nodes? What is the percentage of susceptible nodes in the system? This is a different way to actually kind of see what's going on in the network. This is a different way to actually observe the network. But But again, there's another portion when you talk about epidemiology. And the thing is, people eventually recover. Not everything is a terminal illness. Not everything stays with you forever. Sometimes you recover, and sometimes you have immunity, so you won't get it infected again. So you're no longer susceptible, but you're no longer infected either. And that's considered the recovery state. This is actually called the SIR model, susceptible, infected, and recovered. So the idea is, like, after a certain amount of infection period, you eventually recover from it. And this is that same model, but now with each node recovers after time 3. And now the full graph kind of finds stability in 7 steps. And one more thing, because each node is an individual, if we actually think that certain things have immunity, not everything has the same chance of getting infected simply by a contact. Some people actually have a stronger immune system, some people have a weaker immune system. So that can actually be given to each node. Each node can have so here I call it alpha. Each node has a separate immune system. And here we say, in this model right here, it's like alpha is the number of connections a node has to be connected to before it gets infected. So the one on the bottom left has an alpha 1, so it gets infected immediately, but the one on the bottom right does not get infected immediately because it has more of a resistance. However, now that the 2 adjacent nodes are infected, this bottom right node does get infected. And so here is the same SIR model, simply with different immunities. And rather, with the first, or this is the SI model, there's no recovery in this model, but in the first SI model, the entire system got infected in 4 steps. Here, this is probably a little bit more close to reality. This is a little bit closer to how a real system would be. Here, the entire system gets infected in 9 steps rather than just 4 steps. So it kind of models reality a little bit more, and you can keep on tweaking it. You can keep on tweaking the model until it actually matches reality. And the importance of that is once you actually figure an agent-based model or a network model that actually resembles real life, then you can start interfering with it. You can actually start having these. We can actually start playing with it. Okay, we realize that this part of the system is completely infected. What happens if we cut it off now? Do we save the population or whatever? There's different ways to play with it, and that's the takeaway from it. That's the fun of it. And again, so here where the original SI model was kind of pretty straight linear, you see things are a little bit different here. Okay, so there's going to be a coding portion, so get excited. All this stuff is in an IPython notebook at my GitHub repository called Benjamin Ortiz Ulloa PyData 2018. So let's have fun. Here is the thing. So this is igraph. igraph is actually a C library with Python and R wrappers over it. And it's really important that you actually, so the actual igraph Python library is pretty straightforward to download. You can just pip install it. Plotting is a little bit trickier because you'll need Cairo. So if you don't have that installed right off the bat, you're going to need to deal with that. So this portion right here is just going to explore how to actually play with the graph data. And then I'm going to show some code later on, just a quick example of how to plot it. But right now I'm just I care more about the data first. So we're going to actually go ahead and just load the igraph library. And then we're going to initialize a graph. So here, so you initialize the graph by simply calling the graph method on igraph, or the graph function on igraph. And graphs can actually hold a graph attribute. Right here, a graph can have a name. We want a name. And it can also have information, what kind of graph is this? This is important information that you actually want to stick on a graph. In general, when you share a graph, you want people to have context. You want people to understand what they're looking at. Name it and provide some information. So here I actually provide this is a Hello World graph, and it's a toy graph for this exact conference. And an important thing to say, I'll hover over it. Right here, this is what, if you actually print out the G, or the graph object that you created, this is what you get. It's just it's an object of class igraph graph. So this is right now just an empty graph. We need to add vertices to it. And so we simply add vertices to it, but with a method called add vertices. And you add the number of actual vertices that you want. So I want 4, so it's going to add 4, like 4 unattributed vertex to it. So that's going to be just simply a vertex of 1, 2, 3, and 4. And then you can add attributes by using this method right here, the graph object .vs. VS is how you actually access and read and write vertex objects into a graph. So here I define 3 vertex attributes, name, age, and gender. And I provide it with a list of size n being the number of vertices you have, of these attributes. So it can accept a string, it can accept a Boolean, it can accept a number, whatever you want to put in there. It could store essentially anything. So, and then right here you have a graph vertex sequence. This is what happens when you actually just print out the vertex graph. But the cool thing about these vertices, and you'll see this again with the edges, is this is an iterable. You can iterate through this and actually get the information that's stored in it. And what's stored in the vertex iterable is the actual graph that it belongs to. Like where is this vertex coming from? It gives you the vertex index within that graph, and it gives you the attributes. So here you'll actually see the name, the age, and the gender. And that's how you're going to access and play around with this information. You're going to iterate through the vertices to get the information that you care about. And then we're going to do the same with edges. You can add edges, and the edges accepts a pair of indices, of the vertex indices, and it will just connect from the first indices to the second one. If it's directed, it will just have an undirected graph. If it's undirected, just connect the 2 things. So here, like the first 3, it connects node 0 to node 1, node 0 to node 2, node 2 to 3. And we can also give it an attribute in the same way that we can give a vertex an attribute. It's the graph object .es, which is the edge sequence, and you just provide it like you would actually add like information to a dictionary. You just add it the name of the variable and the actual a list of n equals like the size of the edges or the number of edges you have of information. So here I just kind of made a random attribute called friendship strength from just gave it like random numbers. And this is it's similar to the vertex sequence where you have the graph object, you have the index, and you have the attributes. And again, you want to iterate through that to get that information. And the cool thing, like what's implicit in like edges is that there is a from and a to. Like there's a source node and a to node. Whether it's directed or not, like when it writes the actual information down to create an edge in the graph, like there is going to be a source, there's going to be there's going to be a target as well. And that's like whether it's directed or not, that's implicit in the data. So you can actually just iterate through the edges and actually find which node is the source node and which node is the edge node. And the default is that it's the source node that it provides is just the index of the node you're interested in. But you can use that index to read from the vertex list, right? So here again, like we get the vertex list of all the target nodes from the edge list. So if you print out a graph, you'll get this neat thing. So, bless you. So there's like there's first 4 characters. So there's U or D if it's undirected or directed. You'll have N or a dash. N means it's a named graph, as in the vertices are all named. What follows that is a T or a W for if it's a weighted graph or not, and then a T for if it has a type. Type actually means that the nodes have different types, which is a bipartite graph. So if you look back at the recommendation system, there were people and there were objects, or like there were objects and there were attributes. There were different types of nodes, and that can be actually put into the data as with a special attribute called type. And if you only want the actual, also there's 2 dashes which are just separated. There's the number of vertices, the number of edges, 2 dashes, and then the name of the graph. And if you only want the summary information, igraph has a special helper function called summary. I'll provide everything except the edge lists. Oh yeah, also these are the edges in the graph. It will provide you a quick sample of the edges. Editing the graph. So you can actually, sometimes you'll have to play around with the graph. Sometimes you'll have to iterate it, and at different times you'll need to add vertices or remove vertices or add connections and remove connections. And the way you do that is simply with this method called delete vertices and delete edges. And here we just removed everything from the graph. We created a null graph with 0 edges and zero vertices by just removing them all. And when you want to rebuild things, you cannot. And we originally just created the graph by providing it with a number of vertices, like 4. We can do the same. We can actually create a graph. We can actually add vertices to a graph by providing it with a list of names as well. So we'll do that here, just in a different way to actually create a create a graph. Also, you can utilize the edge sources and target to actually put attributes in your edges. So here I just kind of used the name of the source node and the name of the target node to create a edge attribute called reference or ref to say where is the source coming from, where is the target is. That's just a different way to play around with the data, to play around with the vertex information to create information in your edges. And then you can delete if you have because we deleted the original edge list, but because the graph is the same, it still identifies that there should be a friendship strength, but it gives it a value of none. If you actually want to delete that, you can delete it in the same way that you would delete a dictionary attribute by using the del function. Now, we're going to go through querying a graph. So the actual fun of exploring graph data is actually kind of just traversing it, actually exploring the edges and the nodes and seeing what is connected and what's not connected. And that is called traversing a graph. And that's how you actually explore the graph and the data that's inside of it. So so we're going to actually just kind of create a variable just to help us actually explore this. Claire was a node, the name of one of the nodes. So actually find the ID, or let's get that. There's a selects method that both the edge sequences and the vertex sequences have that help you kind of filter down the sequences to the actual graph that you want. If you provide it with the parameter that is equivalent to the actual attribute that you care about, there's a name attribute, and then give it an equal signs to what you want to find, it will actually filter that down. So we want to actually filter it down to Claire, any vertex that has the name Claire, and it does that. Now we have a vertex sequence that is only with nodes that have Claire as the name. And there's these different Boolean operations. EQ is equal, or you could just use the same, the equal operator. NEI is not equal to, less than. These are pretty, just shortened terms of what they do. So it should be intuitive. So GT is greater than, less than, in, not in. So if I wanted to find, and the way you would actually use this is you would append this to the attribute that you're searching for. So if I want to find all nodes that have age of greater than 20, or all nodes that are in the list of Bob and Alice, you just use you have age underscore less than or name underscore in. And this is what you would have. And then the edges have the same Boolean operators, but they also have just a few more as well. They have the source and target, so whether the source is in a certain list of if the source is in a list of vertex indices. You have within, whether if you provide with if you provide it with a single list, it will give you all connections between the vertex indices that are within that list. And if you have between, if you provide it with 2 lists, it will see all edges that connect vertices from the first list to the second list, independent of direction. So here we're just going to run that real fast. The way you would actually write it out is the same as you would write it out for the vertex sequence selections. And there's also this helper function called incident, which provides an edge list, which provides an index of all edges that are connected to a certain node. Those are incident edges to any node that you're querying for. And then you have another thing called neighborhood that provides you with a list of nodes that a node is connected to. So rather than giving you the edges, it shows you what it's connected to, the actual node it's connected to. That's the neighborhood. And then again, these vertex sequences and these edge sequences are just iterable. So you can actually filter them. You can actually play with them the same way that you would iterate any kind of list. You can use like the filter operation on it as well. So we're going to actually kind of like play with some kind of data in the wild. It's a simple, it's called the Star Wars. The data that we're going to pull is a connection between all Star Wars characters and all the movies that they've been found in. So here Luke Skywalker has been seen in both The Revenge of the Sith, Return of the Jedi, The Empire Strikes Back. It's a simple connection. It's a simple edge list from a person, a character, to a movie that they have appeared in. And we're going to use this to actually kind of create a co-occurrence network. So like what characters have been seen in the same movies together. So we've already been able to build a graph. So let's actually build the graph with data from the wild. So let's kind of create the nodes, the name of the nodes. The name of the node list should have unique names. So it will just be single, like each individual character and each individual movie combined in a single one. And the way we'll actually be able to do that is by using the set operator to kind of make sure that all the values inside are unique. And then we're going to create an edge list, which is we're just going to zip through the actual pandas data frame that we loaded in. We're going to zip through all that just to create the pair of vertices that are connected. And then we're just going to put that in igraph, and we're going to give it a. So when you're playing with bipartite graphs, and if you plan on projecting them, generally you want a type of true and false. It needs a type of Boolean where the false is one type and the true is the other type. And when you project it, it will provide you with two values, the bipartite from one direction and bipartite from the other direction. So if I care about the movies and what characters that are connected by them, I want to see indirect connection between movies. That's one direction, and there's also indirect connection between people, where you get rid of you aggregate all the movies that are between two people, put that into a single edge, and use the actual number of movies that are shared between two people as the edge weight. And it's going to provide, like when we project, it's going to provide us with two separate graphs. So we're going to get Star Wars films and Star Wars characters from the projected graph. And here I just have I'm just going to use that information to push it over. And here's the weight of each of the films, how much characters that they share between them. And I showed earlier that it's important to be able to aggregate or actually get information from the nodes that are connected with an edge. That can be done by simply just pulling the sort, like iterating through the edges and pulling and using the source and target operators. And the reason why that's important is now you can actually get information. Like certain things are important, like how important is this connection for somebody? So here, and this doesn't necessarily serve as a proxy of importance because this is like just character appearances, but like within the actual Star Wars universe, some people are just more prominent than others. And so when you see two people together, one person, you can infer, not necessarily, but the idea is that you can infer how important this relationship is for each character. If one character shows up in all the Star Wars movies and one person only shows up in like 4 Star Wars movies, then that relationship is more important for one character than it is for the other, because that's more meaningful for the other one because it's been shown up that was a greater percentage of that person's connections, or of that person's appearances. Like Obi-Wan Kenobi only showed up in 6 movies, or that's not a good example. Okay, never mind. But anyway, that's why you want to actually store information from nodes into the edges, so you can actually query just the edges themselves. It's just a way to explore. I'm also going to quickly, this is in the repository that I showed. There was some code on how to actually plot with igraph. It needs Cairo, and Cairo kind of pops out into its own little thing. It needs Xcode, at least in Mac. So I'm just going to run this code while I explain it. So this would be the bipartite of the movies. This is the bipartite of the characters, or the projected graph of the characters, and this is a filtered projection of the characters. So if you see the general projection of the characters, you're going to see this thing which the thing on the left is often considered a hairball. It's a mess. You can't necessarily get any kind of insights from looking at it. I guess you could see up here there's a community of people that might matter for something, but in the bulk of the graph you don't actually see. It's hard to actually gather insights. So what you want to do is you actually want to filter it by removing edges that you don't think are important. So here I just removed all edges that were less than 4, and then I came up with the graph on the right. If you just remove all edges and all edges that are less than 4, you'll get a graph. If weight is indicative of importance, you'll only keep the important edges and the only important nodes and the only important relationships by filtering out the ones that are not important. So all that code is in the repository right here. Benjamin Ortiz Ulloa /DC PyData 2018. And then I just want to conclude with some things. I am organizing a conference on December 8th. If you're in DC on Saturday, December 8th, and you're interested in R, maybe consider going to this DC Saturdays conference. There's a lot of cool speakers there. There's somebody who's actually is very prominent in the data visualization and graph visualization world, Katia Ognianova, and I'm a big fan of hers. So I'm actually really excited she's coming. And also, so November the 20th is Trans Day of Remembrance, and our LGBTQ, or Rainbow R, is hosting a datathon to just honor this day and honor the people who have fallen or who have died violent deaths because they were transgendered. We're doing this datathon, so please just follow it using the hashtag TDOR datathon. Somebody scraped all the violent deaths, transgendered violent deaths in Cardiff, and they're thinking about making a slide deck kind of honoring these people. There's other projects as well, so if you're interested and want to collaborate, please check it out. And finally, here are some resources if you want to learn more. This is the Gremlin graph. Gremlin is a traversal language for graph databases, particularly Apache, the Tinkerpop universe. And there's also Neo4j, which is its own database, which is also pretty prominent in the graph database world. So these are 2 resources to actually learn more about those 2 graph database ecosystems. And Katia Ognianova has a bunch of great visualization tutorials for graphs. So take a look at that. And thank you. I hope you learned something. Cool. Oh, yeah.
In your how did it determine how?
Okay, so within a network, with a typical network layout algorithm, the actual proximity doesn't necessarily matter. The way these layouts work is that you want to minimize the number of edge overlaps so you can actually see what's connected. So typically, I mean, it's not necessarily the case. It's often like misattributed. If things are like have a lot of connections, they're going to be closer. But that's also not necessarily always the case, because it could just be arbitrarily like an edge just went to the right, and they're to prevent overlap, and then that will be closer to another vertex. So the layout isn't necessarily the XY of the graph plot is not necessarily meaningful. It's the number of edges between two nodes that is meaningful.
Right, I meant relative distance.
No, that's not necessarily meaningful. Yeah. Yeah.
What's the difference between igraph and network X?
So like network X is written in Python and igraph is written in C. So igraph Python is just a wrapper over the C. I go with igraph because it's just what I know. And I guess people have said that igraph is faster because it's written in C. But in the end, like if you're dealing with like a large amount of data, I would definitely recommend using one of the databases, because it's just in general, if you're working with big data, you probably shouldn't be doing it in memory in the first place.
So there's a graph called force-directed graph.
Yes.
So can we use igraph for plotting?
So force-directed graph is actually just, that's the layout. That's the layout of the image. And that's just like, yes, you absolutely can. Again, like different layouts are meant to optimize different things. And force-directed graphs are, the force-directed layout is just optimizing a different thing. Anyone else? Yeah?
It wasn't related too much to this, but do you know anything about graph convolutions? Like I can't intuitively understand.
Can you, I'm not sure, I've never heard of a graph convolution before, but I'd be happy to talk it over and see if we could like brainstorm it together after this. Yeah.
Convolutional layers like you have on images, etc.
Oh, okay. So you mean like RNNs and like stuff, or CNNs, yeah. Like, I mean, when they're explained with graphs, and I don't know enough about it, so I can't really explain it. But basically, like if you look at this is like my guess, is if you look at a CNN chart, like where you have like the different like layers, I guess, each connection between one layer to the next is a different intuition going into that. Again, I don't necessarily know this field that well, so but yeah, that's what my guess is. Just traversing through it. Cheers. Cool.